Welcome back to AP Precalc. This is lesson 1-3, rates of change in linear and quadratic functions. All right, let's start with linear functions. For a linear function, the average rate of change over any length input value interval is constant. We often think of that as the slope of a line. We've said that so many times now it should be kind of second nature. All right, if you look at example 1 here, we're just going to go ahead and do a whole bunch of slopes. So as I go from that, we've got 7 minus 4. Those are our y values, change in y. 2 minus 1, change in x. And we get 3. Do it again. This time we have 10 minus 7 over 4 minus 2. What does that give us? Like 3 over 2? Already I see a problem here. And last but not least, we do 13 minus 10 over 8 minus 4. That's going to give us 3/4. These would have to be constant for this to be linear. So this is not a linear function. So let's go ahead and answer our question down here. It is not a linear function because the rates of change is not constant. And that's the word we want to use, constant. All right, example 2. We have a quadratic function here. G of x is x squared. Nice, easy one. We're going to go ahead and complete this table down here. So go ahead and pause your video. Go ahead and complete that table, and I'll have it completed when you get back. All right, so there is my first table filled out. I have my output values for all of my input values. Remember, x is our dependent variable. G of x, or y, is our independent variable, also known as input, output, domain, range, all those good things that we've heard in the past. All right, now pause the video again and go ahead and do the average rates of changes over those intervals, and we'll look at those in a minute. All right, there's table 2 filled out. We did our change in y over change in x formula, and we got these. What do you notice about these average rates of change? I'm going from -4 to 0, 0 to 4, 4 to 8. What do we notice? Well, I notice that I'm adding 4 here, I'm adding 4 here, and I'm adding 4 here. Oops, forgot the add. Hopefully you notice that that's not a constant rate of change. It went up every time. Sometimes they'll go down. But when they go up by the same amount every time, that's what makes it a quadratic. So let's answer the question. What do we notice about the average rates of change over the consecutive equal length? Remember, I told you that that was going to be a big thing. We notice that the average rate of change increased by +4 each time. Now we call that increasing linear. Okay? Now, I'm going to go back to the first chart. You might have remembered, you might have learned back in Algebra 2 that if I find the differences of these guys, that's -8, and that's a -16. You might have remembered that if those were the same, that would be a linear model. If we subtract it again, I'm going to get 8. 0 minus -8 is 8. -8 minus -16 is 8. The second differences were the same. That tells us that this is a quadratic function. So see, things build on each other from year to year. All right, here in example 3, we have 3 different charts that we want to look at, and we want to see if these values could be linear, quadratic, or neither. Okay, so a lot of things that we could do here. One of the things you might want to start doing is, especially on a problem like this, is do this kind of thing here, kind of like what we did on the other side. And these are differences. What's the difference between 1 and 2? Well, that's 1, that's 1, that's 1. This one is 1, this is 3, this is 5. So already, like if I was just doing slopes, I could do 1 over 1 because I found the difference of x, I found the difference of y, boom. I could do 3 over 1. I could do 5 over 1. Well, that's not linear, all right? So we could find the second differences, and this time it's 2, and this time it's 2. And then what do we have there? Well, we have a quadratic because the second differences were the same. So we would put quadratic on this one. And by the way, these were positive numbers because we're doing the second number minus the first number. Y2 minus y1, x2 minus x1. Let's try it out here on the second one. We got 1. 4 minus 1 is 3. 5. But let's look at this side right here. That's a 1. That's a 3. That's a 5. Now, if you remember from an earlier video, I told you that this is kind of a big deal when we have an x value. When we're going equal jumps to get to the next one, we don't have to worry about it too much. But on this one, they don't have equal jumps, so we're in trouble because if we would have just went to our other one, it looks like a quadratic, right? And it would have been quadratic if they were equal jumps with the x. But because they're not equal jumps, we should be figuring out the slope. So if I do 1 over 1, I get 1. If I get 3 over 3, I get 1. If I do 5 over 5, I get 1. This is actually linear. So be careful. We learn one thing, and then when we learn something new, we forget about that thing we learned earlier. So we want to check slopes out here. That's when we do that first difference on the right, we're assuming that the jumps in x's were the same. So we got to be really careful when our x's jump by different amounts, okay? All right, let's jump over here to the last one. Look at our x's first. 2, 2, 2. All right, I like these kind. That's a lot better. Let's find our differences. What is that? Negative, no, that's positive 2, 1, and 0. Then we went negative 1 and negative 1. Well, they tried to trick us and give us the option of neither, and they gave us one of each, but this one actually is quadratic. All right, more on concavity. We talked about concavity earlier in one of the lessons when we were talking about our function increasing and decreasing. If we have a function increasing, then all of a sudden turns to decreasing, there's concavity. Same with if it's decreasing and goes to increasing. Remember, concavity is just a curve in the graph, right? So if there's a curve, we have some sort of concavity. But now we're going to talk about concavity with rates of change, which is our slope, all right? So it says the average rate of change over equal length input values. That's important. Our x values jump the same amount. The intervals are increasing if it's concave up for those small intervals, okay? The converse of that is if over the average rate of change, the slope for equal length input intervals is decreasing over those small length intervals. So if it's concave down, your slopes should be getting smaller, all right? Notice that we talked about concavity now between two different forms of how we find it. Increasing values versus increasing slopes, decreasing values and decreasing slopes. And they work a little bit different, so you got to be careful of the words because words matter to us in this class. So let's look at A down here in example 4. All right, we have 3 different functions, k, m, and p. Let's look at each one individually. So let's start with k. We're not going to worry about our x values because we have equal length input intervals. So let's go ahead and look at our y values. All right, we've got -3, -2, -1. Those things are actually increasing. So this would be concave up. So that is definitely one way to look at concavity, but we could also find the second differences, and we would see that both of those are positive ones. And when you have a positive second difference, that is also an indication of concave up. Go ahead and pause the video and you give B and C a try, and let's see where we are. So on B, we see that they are the same, the slopes are the same, which means this is linear and it is neither. Lines do not have curves. If they don't have curves, they don't have concavity. And on C, our first difference, the slopes, you can see that the slopes are decreasing. So from there, you could call this concave down. Or you could do the second difference and see that those are both negative, and those would also tell you that it is concave down.